Welcome back. Is the screen there supposed to be on? Is that TV supposed to be on?
Which TV?
The one right there. Okay. I guess I do exist, even though I can't see myself. Okay, well, we left off looking at sparse Lu factorization, but are there any last-minute questions about the project? I see chuckles.
Sorry, repeat that?
Yes.
I didn't get how we can get rid of this S array. For which, it says in the project description, we can get rid of the S array.
Let's see. That's 4.11 or?
10 and 11.
Yeah, 10 and 11. Let's see. Oh, you don't have to do that. Okay. And if you want to, yeah. So let's see. The S array, if I recall, on problem 4.11 is used to store the output of eReach, isn't it?
Yeah, right.
The list of columns.
Yeah.
Okay. So the S array stores that list of those, say, 3 column indices, right? Well, eReach returns these in nice topological sorted order and all that jazz. It's got that extra phase where it searches up the tree and then it says, okay, I have to move this down to the stack. There's an extra loop there, and it saves this result in this list. But in fact, in the left-looking Cholesky, it doesn't matter what order you do those entries in. You're just doing a matrix vector multiply, and you can do it in any order. It's just a sum of those 3 terms. You're taking this times this, adding to that. This times this, adding or subtracting to that. That scalar times this vector, subtracting it from that. So you can do it in any order. Since you can do it in any order, as soon as if you were to take the eReach code, and as soon as you're to observe, here's a new column index I'm going to put in this list, well, just do the whole work. Just do this entire work here.
So we would have to change the eReach code?
Yeah, you'd have to, yeah, well, you wouldn't want to change it. The comment is you'd have to change the eReach code. Well, you wouldn't want to change it for the other use in the other functions. They'd be broken. But you'd want to make a copy of it and mangle it. Yeah. And rip out the stuff you don't need and just put in the stuff you do need. So if you were to do that, then you would remove a workspace. And you'd remove an extra shifting of that workspace around, because what happens in this list is that there's this stack, right? And you search up the tree, and then you stick it at the bottom of the stack, and you search up the tree again, and then when that search is done, it's stuffed in the bottom of the stack, and so forth. In this S array, that movement, all that data movement is useless. It doesn't really help. The only reason to keep it is so that you have less code to modify. It works just fine. Okay, and so it's optional. You don't have to do that. So that's that S array that you can. That's that comment, but you don't have to exploit that. What you do have to do, and I will look carefully for this. If you're at the kth row and you're trying to find these non-zero entries, you have to use eReach or its equivalent to find those 3 columns. Okay, and then once you find them, if I see you traversing through this list looking for row K, where are you, row K? Where are you? Then you've done the wrong thing, right? I mean, think about it. This list is in sorted order, and when you're at, say, column 42, okay, the first time you'll do this whole operation is on the very first entry. And suppose this is, 47. So here's 42. The first time you do this matrix vector product, it'll be with entry 47 and the rest of the list. So, okay, let's take entry 47. Where are you? Oh, there you are. And then multiply you by the rest of the list, rest of that vector, and then subtract. Right there. And then so the next time you come to column 42, suppose it's entry 53 is the next one. What are you going to do? Oh, well, let's go through and find entry 53. Are you no, you're 42. No, oh, you're 47. Oh, there you are, 53. Well, it's the very next thing, the very next one that you didn't do. Right? So if you just keep track of where you left off, it's just the very next thing, right? I described this a couple weeks ago when I described the project description. So that's very important. If you instead decide, oh, I'll forget that, I'll just look through and find it, it'll work, but it will be asymptotically inefficient and it'll be wrong. And what's the point in being wrong? So please don't do that. Okay. So that's a very minor. That's not a difficult piece of code to write. Let's see. So are there any other questions about the project? Or is it all coming together? This is due today, isn't it, I believe? Yeah. Yeah, I'll be working on the next project shortly.
No rush.
No rush. Yeah, I'll post that this afternoon.
How many more are there?
Let's see. We'll have to look at the calendar. I'll either have, I guess we have time for like 1.5, right? Don't we have 3 weeks left?
More or less.
Something like that.
Like the 21st and the last day of the semester.
Right. Okay. Okay, so this is where we left off with sparse Lu factorization. And the idea is this maps out a strategy for computing L and U column by column. So you're sweeping through this matrix column by column, and you assume that you've computed L11, L21, and L31. And you assume you've computed this U11, and that's the first k-1 columns of the LU factors. And you want to compute the next piece. You want to compute L32, and you want to compute L21 and U22 right there. And so these are the three equations that come out of doing the matrix multiplication for these three positions, for the A12 position, the A22, and the A32. So I've written those equations up top there. And it's three. We can solve these with 3 steps. We can do a triangular solve, do a dot product, okay, and then do a matrix vector multiply. This piece right here is actually very similar to what you're doing right now in the project. Project, is it 5? I've lost the number. 5, yeah. So you're doing this right now, right? This is the left. You're doing a left-looking Cholesky. This is a left-looking LU. All right. The only difference in the left-looking Cholesky is you don't need to compute U. You just need to compute L, because there's nothing up. I mean, this is just L transpose up here for the Cholesky. Okay. So, but there's something we could do here that's different, that we can make this more efficient, and that's this equation here. Now, so on the previous slide, I had these 3 equations on the board. Okay, that was what we saw on the slide back there. And I can then solve them for, let's see, I'm trying to compute L32. I need this. I want to compute U12 and U22. Those are the 3 pieces I need to compute. But now, think of this matrix equation and where this comes from. You'll see in a minute. But I'm putting in the right-hand side the column of A. Okay, this is the A12, A22, and A32. This is just the entire column of A, the kth column of A. And this is, I don't know what this is. We'll find out. This is some solution to some system. I'm making up this system. And this is a funny matrix. This is lower. This piece right here is lower trapezoidal, right? This is the first k-1 piece of the columns of the matrix you've computed so far, and this is identity, and this is is easy to construct implicitly, in the sense that we've got this part of the matrix already. This is just the L matrix, but if you happen to say, well, what's column, I mean, if K is 42 right here, and you're computing the kth column, and you ask, well, what is column 57? Oh, well, that's just, there's just a 1 in the diagonal. And you don't have to look at the data structure to learn that. So, because the data structure is not constructed yet at that position. The column doesn't exist. But you can pretend it's there. So this is by pretend. We can do this. We could do this triangular solve. We could modify the sparse lower triangular solve to handle this matrix just by pretending that those columns are, if it's beyond this point, that those columns are just identity. So this is easy to do. So what does this get us is the next question. Well, these are the three. Let's look at these three equations and write them out. So the first equation is L11x1 equals A12. So that's taking this first row times the x vector. We just get L11x1 equals A12. Right? Just plain old block matrix multiply. And then we get L21x1 plus x2 equals A22. And then we get L31x1 plus x3 equals A32. Now compare those two equations on these two boards. I don't know if you can get them both on the screen up there. This is why people should come to class. Nudge, nudge. Okay, so look at these two equations. And I'm going to box these terms in here. Okay, if x1 is u12, then so is that, but then so is this. And if this x2, if this is u22, well, then that accounts for this equation over here. And x3, well, if we just make this, if we just call this L32u22, then we're done. We have the same set of equations, all three of them. We've got all three of these equations right here represented as the solution to a single lower triangular solve. One of them. So where did the matrix vector multiply? Where did the dot product go? It's all hidden inside. It's all being done by the triangular solve. Okay. There's a lot of equivalences like that in linear algebra. You know, if you gave me a machine that all it could do is multiply matrices together, then I could use it to do anything. Almost. Or if you gave me a real fast machine and all it could do is solve lower triangular systems, and you said, well, I'd like to multiply two matrices together. Well, I can do that too. You just have to recast the work, like here, for example, to get it to do what you want it to do. So what we can do then instead is we can replace these three equations. We don't have to compute this as three separate steps. We could do a single lower triangular solve, and then when we're done, all we have to do is take L32 and divide it by the diagonal, and we're done. We have the next column of L. So that's the left-looking LU. The one thing that's missing here is partial pivoting. But that can be done right now at this step. So what happens, let's see, and I don't really want to go through all of the gory derivations I was showing you. I mean, I've got it in the book. I think I do anyway. What happens to these matrices with partial pivoting? Let's see. Well, I've got it for the 2x2. I've got it for the right-looking case. I don't have it for the left-looking case. I've done it. It's so ugly it doesn't even belong in the book. But the idea is that once you've computed x, the entire x vector, before you do this division right here, it turns out that x2 and x3, this is a scalar, this is the candidate pivot, and x3 is everything else. It turns out now, though, that at this point, I can after I compute x2 and x3, I've done nothing yet that depends upon the permutation for the kth step, that is the kth pivot row. So none of these terms here are dependent upon what permutation you apply to this piece. So I could, in the matrix, L11 it does. So I've got L11. This is the triangular matrix. There the order matters. But here I've got this row vector L21, and then this matrix L31, and then I've got now this vector x2 and x3. Okay, at this point, all I've done is some matrix vector multiplies to get x3, x2, and x3. And let's suppose with partial pivoting, the notion is that you can imagine partial pivoting as occurring, the permutations, the row permutations, as occurring before the matrix even was started to be factorized. And we can view this at this point by saying, well, look, the row ordering of this matrix is independent of whatever computations I've done on it so far. If I decided to, say, swap these two rows, I would still get the same values, just in different positions. Because all I've done is multiply this matrix together to get these terms. And so x2 and x3 can be arbitrarily permuted, as long as, of course, I keep track of what that permutation is for subsequent computations. Here the permutation is fixed and it matters, okay, because there's an ordering here in this triangular solve as to what has to happen. But inside the matrix vector multiply, you can permute a matrix vector multiply beforehand or afterwards, and you get the same result, just permute it. So what if I decide that, hey, x2 is too small? Oh, well, no problem. At this point, I can do partial pivoting. In other words, this column, another way of looking at it is that this column right here of x is that very column I would get if I were to do Gaussian elimination with an outer product method up to this step k, up to but not including k. In other words, if I do LU factorization up to this point k, and I have this matrix A prime, and I want to take this matrix here and grab the first column of A prime and decide, well, hey, I don't like this value. It's too small. I want to go down here and find the largest value in magnitude and permute it up to the top. This column right here is this very column. Now, I don't have the rest of A prime out here. It hasn't been touched. It hasn't been modified. It hasn't been computed. I don't have it. But I don't need it to do partial pivoting. To do partial pivoting, you just have to look at this column and decide, okay, you're the biggest one, put it there. So partial pivoting does not cause any problems numerically. In other words, we don't have to worry about computing extra stuff to decide how to pivot. We just look at the column of x and pick the biggest value. The other thing that partial pivoting is good for here at this point, or that it doesn't break, is the symbolic analysis. Okay, remember the symbolic analysis that we had of the upper bound, A equals QR. We did QR factorization, and potentially we did a column permutation on A first to do the fill reducing ordering. But let's defer that. Let's suppose we did that already, and so let's ignore that. Well, if I decide later on to do some row permutations with a different permutation vector, of course, R doesn't change. This just folds into Q, P times Q. R is the same. R is independent of the row permutations. R is the upper bound on the U matrix. So all the symbolic analysis we did is not affected by the row permutations. Another way of looking at this is that when we did the QR factorization and said, well, is this how is the QR factorization a picture of LU factorization in terms of the upper bound? Remember with QR, I guess I can just describe this rather than draw it. Remember with QR factorization, what happens is every row that takes part in the computation is replaced with the set union of all those rows. So that set union includes, because every row gets modified by every other row, if you will. The householder just wipes everything, makes everything the same. With Gaussian elimination, with outer product, not the lower triangular solve, but with the outer product form, what happens there instead is you take the pivot row and you add it to these other rows below it, where there's non-zeros, to zero these entries out. And in doing so, any entry here appears here. But of course, you could have a 0 there and an entry here in LU factorization. And this doesn't become non-zero. And you could also have this. This entry here doesn't cause that entry to become non-zero in LU factorization, right? Because you're just taking this pivot row and you're subtracting it from here, and from here. And it would cause, if this is the picture here, it would cause these three entries to become non-zero, but these two stay the same. They don't cause, there's no fill at that point. But in QR factorization, it's different. In QR factorization, if you do a householder on this column to annihilate that column, every row gets replaced by the set union of every other row, of all the rows. And so all of these become non-zero. So QR factorization accounts for all that pattern. Well, now think about partial pivoting. What if so QR factorization just splat. It does all of this work. But now with LU factorization, you don't know ahead of time which of these rows you're going to pick, but you're going to pick one of them as your partial pivoting choice and swap it at the top. But no matter which you pick, you can't get more than the QR. The QR is an upper bound, regardless of that row permutation. So that's why the row permutations then don't affect the symbolic analysis for LU factorization. There's no damage to the symbolic pre-analysis. And numerically, it's easy to go down now with this left-looking method, to go down and look at this column of x, x2 and x3, and decide, hey, I've computed x, but oh, no, I don't want x2 as my pivot. Let's pick somebody else. So that's where the partial pivoting comes into play. Left-looking LU factorization with partial pivoting, actually the easier part is the partial pivoting, interestingly enough. The harder part is the triangular solve, but you know how to do that already. We've done that. With one twist. Okay. The twist is this. With permutations, so now we're doing PA equals LU. With these permutations, if I take the A matrix and I swap rows, then I've got to do the same on L. So if I start with, say, A equals LU, and I said, oh, no, that's not what I want. I want to swap some rows. Well, then L has to get permuted as well. In other words, when I do this permutation, when I swap these two, you can look at it here as well. Imagine we're doing LU factorization with just plain old Gaussian elimination. If I decide, oh, I want to swap these rows, I can't just swap the rows here of this A matrix. I have to swap the whole matrix. I have to swap those two rows in the entire matrix, which means I have to swap the rows in L as well. No problem. Well, but now think about the data structure. Think about how this matrix L is implemented. If we are going to use an efficient sparse lower triangular solve with time proportional to the number of floating point operations taken, we need a graph of L in its out adjacency form. We need to know, given if you're at a node, where are your adjacent nodes outward? You know, where in other words, what's the column? We need it column by column. Every column of L we need. So we need it stored by column. But I'm swapping 2 rows. Oh, that's ugly. Imagine now what you would have to do to implement that. If you were to actually now go through, you do this partial pivoting, you know, it's no problem for the A matrix because you can then, when you come to the A matrix, you can apply, when you come to this new column here, you can apply all the previous permutations to it as you wish. Okay, that's easy. We could do that. I don't do that, but we could. So A prime, you could view through a lens of a permutation, all the permutations applied to it so far. That would be fine. I don't do that, but that would be fine. But L is a problem. L is a big problem because go through L and swap 2 rows, good luck. I mean, that's just horrifically ugly. You'd have to look through every column and say, well, are you okay? Are you okay? No, oh, there you are. And are you the next? Oh, there you are. You know, you have to look through the entire matrix. That's ridiculous. And it would obliterate, since you'd have to end up looking through the entire L matrix, which far outweighs the time taken to do the sparse lower triangular solve. So you have an amount of work that you're just doing, searching, looking through stuff, finding stuff that is far above, asymptotically, the work it takes to do the LU factorization in the first place. So this is very unattractive. So what do? Well, we punt. We don't permute. Why bother? Why bother permuting? I mean, why bother permuting L? Because here's why. Here's what we can do instead. What's so special about permuting these 2 entries in the column of L? If I could just keep track of the fact that, well, hey, when I was at step 42, row 27 became the 42nd pivot row. That's really all I need to know. In other words, when I come back through this column, all I need to do is make sure, when I'm doing the lower triangular solve, all I need to make sure is that this non-zero modifies the correct non-zero in my target vector. So it doesn't really matter what I call it, as long as I call it consistently. I mean, so what if I call this 47 and tomorrow I call it 53? I don't want to do that. I'll just this whole row of the A matrix. It could float around up and down all over tarnation. Tarnation, that's a strange word. I don't know where it comes from. Anybody know? You've heard it before, right? It doesn't really matter where this row lives. As long as I keep it all together. That is, this entry in L has to correspond to all these other entries in this row. So all we got to do is keep this row together and we're fine. So why renumber it? Let's use a consistent number for this one. And what's the best consistent number? Well, just the original row index. In other words, what I'm going to do is for the A matrix and for the L matrix, I'm going to work in the old space. That is, all the integers that I store in the data structure, I'm not going to go back and try to update them and say, well, now you're here, and oh, you know, you're over there, now you're here, and try to change the data structure. No, I'm going to use the idea of a lens. I'm going to keep my data structure untouched, I'm going to keep all the row indices. So let's keep all the row indices in reflecting not the permuted space, but the old space. So now we have to remember that every row index in the L matrix is not the real row index of L. It corresponds to the row of A from which that row of L came. Okay? So L now no longer needs permuting. Because if I store inside L this old row index, if this row decides to go down here and then move up here and then finally become the 42nd pivot row, fine. It's still row 47 or whatever it was at the beginning. It moved around and then finally laid to rest here at this pivot row. Who cares where it came from or where it ended up? All I care about is a consistent name for it, 47. I'll call you the 47th row, even if you become the 42nd pivot row. Fine. Okay, so when that happens, then we've got a rather funny situation in our. We have to adapt the lower triangular solve. Okay, the lower triangular solve has to go through some adaptations. And you might have to go through some adaptations as well. Not you personally, you, the matrix, you. Okay. All I really need to keep track of is when I'm at the kth step, which row I do I choose in the A matrix to become the kth pivot row? That's all I really care about. So this row I may have moved up and may have moved down and may have got swapped around and finally it becomes the kth pivot row. All I need to do is log that fact. Keep track of that fact, that it's the ith pivot row reflects this column K. This means then that, say, this entry right here, which has already been chosen as a pivot row, this was some previous column K prime, and this is some previous row I prime. I and K are not the same in the data structure. Now, once L is all finished, I'll go back and fix up, the permutation will be complete. And then I can go back over one pass and I can replace I with K. Because this really is row K, right? That's the kth row, or K prime. This is the kth row. This row I in the old matrix will become row K in the matrix L. Right? Because it's the kth pivot row. It sits right here. So this is row K of L. So this is K of L, but it's I of A. Okay? It's sort of like trying to keep track of a bunch of people, and you get confused trying to keep track of maiden names and married names. And what if a person gets married 7 times? You know, like Elizabeth Taylor, right? Doesn't she just keep her name Taylor, right? You know. So this is like Elizabeth Taylor here. It's like row I of A. It's Taylor of, it's Elizabeth of Taylor. Okay. And no matter how she gets permuted and swapped around, that's sounding rather personal, I guess. At the very end, there's her last. Oh, this is getting morbid. I'm sorry. At the very end, there's a position for this row I, and it's at the position K of the L matrix. But this position is not known until we get there. And so as this row is operated on, let's just use this old name here, row I of A. And let's, again, also use this name. So all the row indices in L are old. But the columns are new. Okay, so if I'm at, now here's the trick. Here's the tricky part here. So if you're at a column, let's just not call it K prime, let's call it J. So imagine now you're trying to do the sparse lower triangular solve. And let me redraw J over here. So now imagine you're trying to do the lower triangular solve. And you're asking, okay, I'm at node J. And you're doing the reach. So you're at node J and you're asking, who can I reach to? Well, who is this? This is some row index I. But it's row I of A, not of L. So who do you get to here? Well, we've got to remap this and ask the question. We have to then, at this moment of the depth first search, we'll grab out the row I and we'll say that, hey, column J, you're adjacent to I, but oh, no, you're not I of A. Who are you of L? We have to go through an inverse permutation. That's all. But this inverse permutation is well defined for the first part. It's not well defined here, but it could be partially defined. Let's see, what is it that I do? So we can find out that, in fact, if you're down here, if you see a row I and you're down here, and you want to ask, who do you get to when you're doing the reach in this code? Well, in L, you get to an implicit identity matrix. So if a row I of A has not yet been chosen as a pivot, then you know that, hey, you're just in this, you're just in this implicit identity. So we're just going to make up a column for you anyway, and there's no outgoing edges of that magical, mythical, made-up column, because it's identity. Otherwise, it's some column J prime, which is the PINV, the P inverse of I. Because I have to go from old to new. That's an inverse permutation, according to the notation I have in the book. I have to go from the old row of A to a new row of A. If row I of A has been chosen as a pivot, and now this is another column with further out adjacency edges. If, on the other hand, row I has not yet been chosen as a pivot, then that's a row down here. It's not a row up here in the L11 matrix. These are all the pivotal rows. L11 are all those rows that have been chosen as pivot, and L21 and L31 are those that have not. So I can easily determine, here I need to do a further search. I do the inverse permutation, and out of PINV I get, oh, this is your column. Row I, oh, you're the fifth pivot row. So then to find, so this is 5. So to find the adjacency, I need to go from, say, row 42 is the fifth pivot row. Well, if row 42 of A is the fifth pivot row, then I have to go to node 5 and look out from there to do the depth first search. So there's just one little twist then. All we have to do is say, well, hey, I get a row index out, and then say, well, who are you really now? And that's the lens. We're looking at the L matrix now through a lens. We're not trying to permute L as we go. It's too hard. We're leaving L alone. We're putting in L all the old row indices corresponding to rows of A. But whenever we grab out a row index, we can translate it on the fly. Okay, so that is easy to do. That's just a lookup. Rather than trying to go through and mangle the data structure, that's incredibly difficult. So that's all we've got to do to make this triangular solve work, is we've got to remember that, oh, the row indices in L are kind of weird. They're old, and to get what they really are, we have to do this permutation. And furthermore, we want to do all of our other computations for X and for A. You see, this is also old. The column of A, all these are old row indices. We could permute them if we want, but when we pull them out of the A matrix, they're all in the original row. If I see row 7, that's row 7 of the A matrix, so that's in the old space. And the same thing for L. All these row indices are in the old space. And then X, then, would be most naturally stored So that if I say a row 5 of X, that's not row 5 of the L matrix in the final permutation. It's 5 reflecting row 5 of the A matrix. So let all of our row indices, for all of our gather scatter, for all of our work as we go, be done in old space, not new space. Okay, not old spice, but old space. So this is the left-looking LU as a MATLAB implementation, but this does the actual this does the actual permutation. So the code's going to be a mimic of this. Here's the sparse triangular solve with, this is the L11, L12, and L13 matrix right here. The first K-1 columns of L. This is padding on, you notice I'm not even attempting to use sparsity here in this MATLAB prototype. This is padding on the identity matrix right here, this piece. Do a triangular solve with the kth column of A, but now this is bluntly permuting everything into the new space. So this is doing something different than what the code is going to do with the permutations. Then the x1 vector becomes the kth column of U. We can do the permutation and then find the pivot row and then physically do the swap, actually move the data in the L matrix and in the X matrix, and then the X vector then becomes the kth column of L once we divide by the pivot. So this is a rough prototype of the numerics of the code, with one exception. This is constantly swapping rows. We don't want to do that. We want to leave this alone. We want to postpone this work. And all of this work, every row index here, we want to rip out and say, no, 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 no. I don't want to use constantly juggling row indices. That's too complicated. I want to instead do all of this computation, every single line of this code. Every row index that I see will be in terms not of the current permutation, which is constantly changing anyway, but in terms of the fixed ordering of the rows of the A matrix. And I'll translate on the fly as needed. Okay, so now we get to the code. So you see what has to happen then. In the triangular solve, let me just draw a picture just now of the triangular solve, because it's the triangular solve where the worst of the work has to happen. If we're at a column J and I see a row index, I'm going to see two kinds of row indices. Right, I'm going to see a row I that's been chosen as a pivot, and I can keep track of that. I will say that pin of I1 will be some K1 if this is column K1. Whoops. Let me draw it like this. And in particular, this is in the range 0 to n minus 1. If it's minus 1, that means it's not pivotal. It's not yet chosen, and that means it's in the L31 or L21 part of the matrix. It's down here. It's a pivot candidate, and it's not yet chosen. This right here is our implicit identity. This is the L we've computed so far. This is our implicit identity. And if I see a row index I2, I1 might be larger than I2. Okay, it's a row of A, not of L. In the final permutation, the permuted row I1 will appear before I2, but it doesn't yet necessarily. But PIMV of I1 has been modified to be equal to K1. Otherwise, I will say that, well, if I2 is not yet pivotal, then PIMV of I2 will be defined as minus 1, or non-existent, not computed. Then in the depth first search, if I try if I'm at J and I want to know, well, okay, who do I have to go through from J? I go to K1 if I see the edge I1. K1 is the PIMV of I1. Otherwise, if I see I2, I don't really know what the name of this node is because it doesn't have a name yet. It's not chosen yet. It's not pivotal. Row I2 becomes which pivot row? I don't know. I have no idea. But I don't care because no matter which node it is, in the current graph of L, there's no outgoing edges to it anyway. Right? It's just a dangling node for which I have no work to do in the depth first search. Right? All I have to do is say, well, okay, fine, you're there. Now, in the result of the depth first search, I do need to note the fact that, hey, I visited this node, and I visited this node, and I visited this node. But this node doesn't have a name, so how do I refer to this node? As I2. So that means I have to refer to this node as I2. And this node as whatever, I0. Whatever was the jth pivot row, that's going to be the... So I have two. Every node has two names. This node has two names, I1 and K1. This one has I0. Maybe I should call this instead of J, K0. Row I0 was the pivot row chosen at step K0. Row I1 was the pivot row chosen at step K1. And row I2 hasn't been chosen yet. So this has no name in the new space yet. So the only consistent naming I can have for all of these rows is I0, I1, I2. So that's going to be the result of the depth first search. That's going to be what I'll do the gather scatter with. So when you're doing the triangular solve, you have to scatter this work into the right-hand side. You can't call it by the new name because the new names aren't done yet. You can call it by the old names. Okay, so that is what's going to happen. There's going to be this partially constructed row permutation. Okay, and if we find a row for which pinv is -1, then it looks like this. It's a dangling node. I do have to reflect the fact that I reached I2. I reached this node, but I need to call it by the name I2 and note then that, hey, it's got no outgoing edges. So let's look at then the code and see how this plays out. Well, and we won't have very much time, so I'll probably just get through the first phase here. This is just all boilerplate, right? There's nothing in here that's very difficult to understand. It's just checking the input arguments, getting the symbolic analysis here, getting out the upper bounds of the non-zeros in L and U, which, by the way, might just be a guess. If I do the QR analysis, these are precise upper bounds. They cannot be exceeded. But that's a lot of work. What if I just wing it? That's not a problem, turns out. Because the L and the U matrix are growing column by column. And if I run out of space, I just make the space bigger, just like the dynamic table algorithm. So that's what's going to happen here. X is our double precision work array that we're going to do the gather scatter out of. Xi is the workspace for the stack and that sort of thing. And then I'm allocating a struct here which is going to contain the numeric factorization, which we've already done for Cholesky and QR. Run out of space if we need to. And then spalek these two matrices L and U. Okay, two n by n matrices with LNZ and UNZ, and I forget what these numbers are, but this asks for a compressed column matrix with numerical values. These two parameters, and then a pinv, a row permutation, which is part of the final data structure. And then if, of course, I have a memory failure, then I free everything and return. And now I can start the work. Now I can get the column pointers for L and U, which are not going to move around. The contents I'm going to define, but the data structures doesn't move. And then and then I assign this to 0. And I don't know why. I guess I was paranoid that calc, a double precision 0, is all bytes of 0, and I should have just put a calc here and ignored it, but I assigned it here because I was a little paranoid that I don't know, IEEE. I could have assumed IEEE arithmetic, where 0, the floating point 0 is in fact all bytes of 0 anyway. So that was kind of odd. I don't know why. I guess I was being persnickety. Anyway, so it's 9:20. I've got a lot more to do with this code, but there's 1 page, 2, 3 pages of code. That's it. And we'll have to go back also to the triangular solve. 4 pages of code. We'll also have to go back to the triangular solve and understand, and where is it? We've seen this code before. We've seen the triangular solve, but remember when we did the triangular solve, I said, oh, well, there's this extra little thing in here, this p inverse. Just ignore it. It's null. Right? Well, now it's not. Now we have to worry about it. And so I'll go back to the sparse triangular solve and say, well, now how do we manage this viewing L through a lens? That's what this right here does. And we'll do that then on Monday. See you then. Thank you.